Okay, hi everyone. This live streaming is for our midterm examination. So it was on April 18th. So already almost 2 months have passed, and we are quite close to the end of our semester. So I have finished the scoring your answer sheets, and unfortunately still we have only one remaining lecture slot, so maybe it's not very convenient for us to have an additional session for our midterm examination. So in this live streaming, I wanted to just explain what is the answer of your homework, your midterm examination problems. So you can check the correct answer and check your score, and that will accelerate our discussion about your finalized score. Okay, so let me just directly move to our homework problem 1. Okay, so in this case, yes, we have one crystal silicon. Yes, and the first problem is to calculate the shortest distance between two neighboring silicon atoms. So it is given by just a vector corresponding to a quarter, and quarter A. That is the minimum, the shortest vector connecting two neighboring silicon atoms. So the distance becomes just yes, this number, and you know this A equal to 0.543 nanometer. So when you correctly calculate it, then you can get the full score. And calculate the density of silicon atoms. So you have done it as a homework problem, and yes, so the answer is simply given by 5 times 10 to the 22 per cubic centimeter. Okay, so then now let's move to our homework examination problem C. Yes, here we have certain conditions for like this: y equal to 0. So when we have y equal to 0, yes, now we can make it 0 or we can make it 0. However, in this case, in this second case, it is difficult to find such a condition. So our you know our second possibility is not available. So only when we have I equal to minus k, then we will have the answer. So when you calculate the areal density of silicon atoms, then the answer would be 6.78 times 10 to the 14 per square centimeter. So since we are working with areal density, so you should have the correct correct unit, and instead of this y equal to 0 plane, now we are asking the answers with x equal to y plane. So quite easily, so you can just repeat this procedure. So you say that yes, this and that are the same, and this and that are same. In this case, the case is your I should be equal to j, and in this case, yes, in this case also you have to have I equal to j. So when you just insert it, then you will get the solution. So many students have made mistakes about calculating the final answer. So when you make it, then you just underestimate it, because you are some of you counted on atom. For example, if you have this condition. So this is a unit cell. For example, the size or length is given by A, and this is B. Just oh, I think that is too much exaggerated, but anyway, so this is square root times E. Then you may have certain atoms. So yes, so in this case, so since we are now working with areal density, if there is a certain atom here, then it should be regarded as just a full one atom belonging to this rectangle. However, some of you just counted it as a as a just volume density and just count it as half of it. So that is not the case. So the correct answer would be 9.6 times 10 to the 14 per cubic centimeter. Oh, no cubic centimeter, square centimeter. So okay, that was the first problem. And let's go to the second problem. Okay, the circuit schematic can be easily drawn as this way. Yes, now we have I in, and it has the amplitude 1 milliampere, and here we have, of course, here we have 0 node, and here we have out node, and yes, we have parallelly connected. Yes, so there is R0 and RD. Yes, both of them have 2 kilo ohm and 2 kilo ohm. So if you have drawn the schematic in this way, then you will get the answer. And calculate the DC voltage of the out nodes. In this case, some of you, actually many of you made mistakes. So here we have, yes, the direction starting from out node and toward this 0 node. So this is the correct direction for our current source, and so no, this is the original schematic, and if we just calculate the equivalent resistance of two parallelly connected resistors, then it becomes 1 kilo ohm. So since we have 1 milliamp flowing through this current source, so quite easily now you understand this would be the direction of your current. So there is a ground, and here we have 1 kilo ohm resistor and 1 milliampere is flowing. However, since the direction of your current is like this, so you will have the voltage drop of 1 volt. So starting from this 0 volt, you will have further 1 volt voltage drop. So voltage at this node should be minus 1 volt, not positive 1 volt. So the answer should be minus 1 volt. Okay, then now here we have to see the DC power delivered from the current source to the resistors. That is, when you calculate the power, dissipated power, so when we have um, Sorry, I got a phone call. Yes, so let's come back. So when we calculated the DC power, actually, when we just calculate the DC power, then how does it look like? So here we have a current source, and its current direction is given by 1 milliamp, and this is downward direction. However, here we have 0 volt and minus 1 volt. So power can be calculated by the P can be calculated by this simple rule, I times V. So I is given by 1 milliamp, and voltage is just given by minus 1 volt. So when we calculate it, then we will have the power dissipation given by minus 1 milliwatt. So what is the meaning of this negative sign? So this negative sign represents that the DC power is delivered from the current source to the other circuit component. So the answer for this first question is 1 milliwatt. And when you calculate it, so for other two resistors, then you will have a positive dissipated power. So for each of them, the power is just given by, yes, this is the answer. Okay. Then now let's go to our final problem. Now, up to now we have thought that this RD has the value of 2 kilo ohm. Instead of that, now let's say that we have certain value of R. Then what will be the power dissipated by our R? So now you can understand, just following the same procedure, then we will have just 1 milliamp, and here we will have a certain equivalent resistance that is given by just 2 kilo ohm multiplied by R divided by 2 kilo ohm plus R. That is the equivalent, yes, equivalent resistance. So in this case, yes, still we have, yes, 1 milliamp in this way. So the voltage of our out node now simply becomes by minus 1 milliamp multiplied by 2 kilo ohm multiplied by R divided by 2K plus R. That will be the out voltage. So for our resistor R, so now when you consider this R, yes, it has R, and the voltage difference is given, then what is the power dissipated by this resistor R? That is simply given by the square of voltage difference divided by our resistance R. So yes, now we will have all of these contents. So now we will have, yes, when you just make a product between 1 milliampere and 2 kilo ohm, yes, then we will have just 2 times R and 2 times 10 to the 3 plus R. That, of course, all of the quantity is written in the SI unit. So when we take the square of this voltage, so then we will have, when we just take a square of it, then we will have 4R square and 2 times 10 to the 3 plus R and its square. and divided by R. So what happens in this case? This R is gone and R is gone. So this is the power dissipated by our R resistor, and it has of course the unit of watt, and of course R is written in ohm unit. Okay, this was the problem 2. And when you go to the problem 3, so the problem 3, the essential point of our problem number 3 is identify where is the real junction. So here we have a p-type well. So the area beneath this p plus region, or this p plus region, they do not contribute to any kind of a p-n junction. So there is no junction at all. Then where can you find the real junction? So p-n junction occurs when p-type and n-type materials are meeting together. So now you can understand the actual junction just occur is beneath of our n plus region. So here we have n plus region. If we just make a two-dimensional cut along this way, then we will have, yes, here we have n plus junction, and there will be p plus junction and p plus junction. Yes. So this is corresponding to our this shaded one, and substrate itself, or anyway the well covering all of them is given by just p-type well. So this is not a valid junction, or this is not a valid junction. Only this guy is the valid junction. So the answer for your first problem A is given by simply the product between D times L. Many of you introduce something like G in your answer. However, there is no, for example, yes, this distance is given by G, and this is G, and here we have D. Yes, this D is important, and this G does not play any role in this calculation. So the answer should be 80, yes, square micrometer. So using this one, the answer of a second problem B is quite straightforward. So you will have 96 femtofarad, and now we are in C. We are talking about peripheral of our junction. Where can you find the junction? Yes, this is shaded one. So then what will be the perimeter of this junction? Yes, this perimeter of n plus region, this rectangle can be regarded as our region. So the answer would be, yes, so the length itself will be just 2 times D and 2 times L. So in this case, yes, this guy provides us 80 micrometer, and this one gives just 4 micrometer. So when you use this one, yes, so we will have additional contribution like 8.4 femtofarad. So the final answer will be this area contribution, and this perimeter contribution. So we will have the 104.4 femtofarad as an answer of this question. Okay, then let's go to problem 4. In this case, we assume that there occurs a certain depletion layer whose side length is given by 75 nanometer in both of p-type and n-type. So it is quite easy to calculate just so q times 10 to the 17 per cubic centimeter times 75 nanometer. So when you correctly calculate it, then in the unit of coulomb per square centimeter, you will have 1.2 times 10 to the minus 7 coulomb per square centimeter. So that is quite easy. And also, so you know this relation. So this is simply given by rho times epsilon. And yes, since we know this q is simply in this case simply given by either positive q times 10 to the 17 per cubic centimeter or minus q times 10 to the 17 per cubic centimeter. And you know this epsilon is given by 11.7 times epsilon naught, and the approximate value for epsilon naught is given in our first page. So from this one, now you can understand, yes, when we just have this electric field, then yes, this length scale is 75 nanometer, and this length scale is also 75 nanometer, and using this given calculated slope of your electric field, now you can calculate this uh, this triangle as a form of your electric field. And yes, the area beneath of this curve, yes, the shaded one, yes, this is corresponding to the voltage difference. The answer would be 8.688 if we keep the first four digits. So anyway, so now when we introduce a reverse bias of 0.1 volt, then what will happen? What will happen to this potential difference? Is it increased or decreases? Of course, it is increases. So that will be the increases potential difference. So in order to support this enlarged electric field, then we have to have wider depletion. So yes, so now you can understand when depletion width is slightly increases, and also peak electric field is also linearly increases. So yes, so compared with 75 nanometer, if we have widened a depletion width for single side, then its square is corresponding to the ratio between our previous one and increase one. So from this one you can find that increases W. So some of you just took the linear relation, but that is not correct. You have to understand this second order dependence. then the answer for this question will be quite easy. So once you know the W value, then this W value also Q times your 10 to the 17 per cubic centimeter multiplied by your newly calculated W value will give you the answer, and the answer is simply given by 1.26, yes, 72 to the 7 coulomb per square centimeter. So you can find that the increase is not that much. So it is only because we have already quite a large built-in potential, and the additional potential is just part of it. So the effect or increase of our depletion width is not that much dramatic. So let's go to our problem 5, and this A is quite simple, and you can immediately find that yes, 750 millivolt satisfies this number. Yes. So and when you go to the number B, so let's say that actually my original intention was start from 1.225 volt. So assuming that 750 millivolt is assigned to this diode, but you know that when you just read this problem, so it just says that you have to start from the answer of homework A. So many of you start from yes 750 millivolt. It's okay. So let's assume that you start from this one. Then what you can get is when you apply the Newton method, then your answer is of the first Newton iteration and second Newton iteration is always stated that you have to increase corresponding to almost quite close to Vt. So your answer should be 775 millivolt, but anyway approximate value, all of approximate value are acceptable. So for example 776 millivolt. After that you will have 802 millivolt. That will be the correct answer. Of course, I'm willing to give you the full score. When you start from V out equal to 1.25 volt, but unfortunately, none of the students succeed to give the correct answer when the students start from 1.25 volt. Well, anyway, so that is the answer when you start from this 750 millivolt. Okay, so this is the final one. Okay, so ripple is given by this difference. Yes. So simply speaking, when this discharging phase, this diode is just neglected, and previously initially charged capacitor whose initial voltage was 3.6 volt is discharged through our resistor. So when we have a certain time difference, yes, so between this time difference, we don't know exactly what it is, but yes, we have certain certain this discharging. So our goal is just to increase our capacitance. So finally, the behavior of our ripple just looks like this. So some of you just simply thought that okay, the ripple was 2.6 volt, and now I wanted to just have 2 0.2 volt. So 13 times reduced value of our ripple, so or reduction or discharge. So some of you simply wrote in this way. So 13 times larger than our previous value. Of course, that just to assume that this behavior is simply linear. So that is not a correct answer, but I gave you a partial credit on this answer. And the correct one can be obtained when you just assume this exponential decay. So now you can understand this one. For example, let's say that this is given by this time difference is given by T naught. We don't know exactly, but we can well estimate in this way. Starting from 3.6, it ends up with 1.0. So this decaying rate is given by exponential minus tau and T naught. So of course we know that this tau is given by 1 millisecond because RC product between 1 kilo ohm and 10 microfarad is given by this way. So starting from all these known values, then now you can find what is T naught. Yes, once you calculate this T naught, then now you just keep this T naught and assert that your decay should be now the voltage after decaying should be 3.4 volt. So now you say that yes, there is a certain time scale which is given by here in this expression, and you find that the tau should be larger than certain times. So actually it should be almost 22 times than the previous tau. So now we have to have tau should be increased almost by a factor of 22. So the way we can increase this RC delay time is now, yes, increasing this C. So eventually the correct value or best Schuster value will be about 220 microfarad. However, this problem is just for a simple estimation. So if your answer is reasonable, then I gave you certain partial credit, but I think that most appropriate answer would be 220 microfarad in this case. Okay, so that was the simple explanation about answer of your midterm examination problem. So I will soon upload your individual score to our GEL system, and of course you feel that there is something wrong, then okay, then please then let me know. Then we can make an appointment for checking your score and finalizing it. Okay, so if you have any further question, then please send me an email. Thank you. Bye.